안녕하십니까. 대한수학회 키아스 대중강연을 시작하기에 앞서 유튜브로 참석해 주신 여러분께 감사의 인사를 드립니다. 저는 이 강연의 자장을 맡은 한국외대 김영록입니다. 이제부터는 영어로 진행하겠습니다. Hello everybody. Before we will start KIAS public lecture in KMS, thanks to everybody attending in YouTube. Let me introduce Professor Brandon Hassett in Department of Mathematics, Brown University. He is currently a director of ICERM. He will give a lecture about big data and computations in arithmetic geometry. If you have any questions, please leave your questions in chatting box in YouTube in English. Please keep. Now, Professor Brandon Hassett, please give your lecture. Thank you.
Thank you very much. I hope you can hear me. I'm really honored to be here this morning on your time, tonight and my time. I really appreciate the Korean Mathematical Society invitation to give this lecture. And I look forward to seeing you sometime in the not too distant future in person. I really enjoyed my time visiting Korea in the past, and I'm very keen to return at some point in the future. So the theme of my lecture today is to talk about big data and number theory and arithmetic geometry. And part of the point I want to make is that big data is not something that's new to us in this field. And much of science and the development of fast computers and the development of systems that can capture data from consumers or through other processes have changed the face of science. But we've been using very large data sets in number theory for an extremely long time. And so part of what I'd like to do is to lay out this history and lay out how the compilation of large data sets has really informed number theory from the earliest stages, and to explain to you also how that tradition continues today through the work of the Simons collaboration that I participate in. So let me get started. And so I'm going to talk about historical big data. So big data in the distant past that informed a lot of important results in number theory. And so the first class of big data I'd like to talk about is tabulations of prime numbers. I'm sure almost everyone in the audience knows that a prime number is a number that is only divisible by 1 in itself. So the simplest prime numbers, of course, are 2, and 3, 5, 7. And so these are really important for factorization and for understanding the structure of the integers. And for a long time, people have worked very hard to try to give complete tabulations of prime numbers. Of course, it's been known since the ancient Greeks that there are infinitely many, so you can't have a book that has every possible prime number. But you can try to list a very large collection of them. And so there are infinitely many, but you can try to list them all up to a certain value. And one of the earliest instances that I found of this, there are probably many earlier examples I wasn't familiar with, is in 1776, an Australian mathematician, Anton Felkel, published a table of all prime factors of the numbers from 1 to 10 million that are not divisible by 2, 3, or 5. And I'm curious to see whether he actually computed up to 10 million, because there are a very, very large number of primes up to 10 million. One thing that you might think about as a quiz is exactly how many. If you look hard on a Google search, you'll probably find the answer, but try to make an estimate based on your own intuition for how many primes there are up to 10 million. There are a large number. And so this was a very serious attempt to tabulate prime numbers, but he only got up to 408,000, which I think is still very impressive Of course, in 1776, they did not have cloud computing or computers or calculators. And I don't even think they probably had any mechanical computing machines that could make this. And so this is really one person in an office with a piece of paper computing examples. And so this was published. So I gave this excerpt for you. I guess this is probably a picture of the person doing lots of work on prime numbers. And I recorded the first page of this manuscript. So this is available actually through the Göttingen Digitalization Center, which is a really wonderful resource for historical mathematics. Has many important documents for centuries back in the history. It's one of the leading world's leading mathematical centers. And so this was not the last word on tabulating primes. One of the most famous instances of prime number tabulation was done by Gauss, the famous Gauss, CF Gauss. He didn't publish tables as far as I know, but he explained his work in letters and left behind notebooks. And so here are some notebooks from his collection, again from the Göttingen Library. And starting in 1792, 1793, when he was, I think, 14 or 15 years old, he undertook trying to understand prime numbers and what patterns they have. And so there's a little hint here at the bottom of what the answer might look like. And so basically his strategy was to, whenever he had some free time, he would knock off all the primes between 1.9 million and 1.9 million, 10,000. And over a course of 50 years, he got all the way up to 3 million. And as far as I know, most of this work, at least in terms of the prime factorization, was done by hand computation. And so here are some excerpts from his original notebooks. And so he wrote letters in the 1840s explaining what he discovered. I don't think this work was ever published by him in his lifetime, but it certainly turned to be influential in the future. So we never get tired of big data and primes. And so Dan Lamer produced another really very impressive collection. And so his collection was published in 1914, and he did actually get all the prime numbers up to 10 million. I wonder if he read Fekel's manuscript from 1776 and took it as a challenge. It took almost 140 years to finish what Fekel started. And so it was a major undertaking, but it was eventually done. Obviously, Lamer in 1914 had access to a lot more techniques for doing computation than were available in the 18th century. Certainly, there were mechanical calculators that were available that could help simplify analysis. And so it was a serious undertaking, but much easier than it was 140 years before. And so this book was published in 1914, and I think I included the last page of the book. Yes. So this is a page of the primes going right up to 10 million. And so it's a very impressive table, and this is the last of 133 pages on this topic. So if this isn't big data, I'm not sure what is. And so this has informed the research in number theory for a very long time. Let me show you how all this tabulation developed into theory over time. So prime numbers aren't the main thing, but I wanted to show you how all this data analysis led to some really important mathematics. And so what I'd like to do is I'd like to consider the function that counts prime numbers. And so this is a function pi of x for prime, and it's just for a number x, which could be either an integer or a real number. It doesn't really matter because you only pick up the integer primes less than it. You just count all the primes. And so if x is equal to 10, you would count, let's see, 2, 3, 5, 7. So pi of 10 would be equal to 4. So let me just write that here. Hopefully I did the calculation right. And so we're interested in understanding how this function behaves as a function of x, and specifically how quickly it grows. So as x increases, we know that the number of primes will increase, but exactly quantitatively how quickly. And in fact, one of the main, I think, points of influence of Fekel's work in the 1770s was Legendre conjectured the growth rate. And I'm going to clean up his guess a little bit. He actually proposed a number of different asymptotics, but I'm taking the best one for your purposes. And so that's explained here, that the number of primes is equal to x over the log of x, the natural logarithm, minus 1. One way of interpreting this is that the probability that a given number be prime is roughly 1 over the logarithm of that number. Now, Gauss's work was not in, it actually gave an improvement, a refinement to what Legendre indicated. And so that's demonstrated here in this formula. And so he gives an integral formula for the growth in the number of prime numbers, taking the definite integral of 1 over the logarithm of u. And so this is another way of basically saying that the probability of a number being prime is 1 over the logarithm. Maybe I'll write this. So the probability of being prime is something like 1 over the logarithm of x. And so it turns out that, at least from an asymptotic or a growth perspective, as you go out to x into infinity, these give you the same asymptotic. And this was actually proven in 1896, 120 years after those tables were put together in the first place. So this was a major result by Hadamard and de la Vallée-Poisson. This used all of the mathematical ideas that were developed in the 19th century, and in particular, complex numbers play a huge role. In the public lecture, I've decided not to get too deep into complex analysis, but all I'll say is that it's remarkable how basic properties of integers really boil down to a detailed understanding of complex functions. I left out a really important part of the story, and maybe I should mention that, at least in my handwritten notes. Another mathematician, Bernard Riemann, gave a detailed analysis of the error terms of these things, of these estimates. And that remains one of the most important problems in mathematics, how to quantify the errors in these estimates. So he made a very specific conjecture on how large these estimates are from the ground truth of the number of primes. And this is one of the biggest open problems in mathematics right now. And so the error terms, they're still wide open. That's a problem called the Riemann hypothesis. So the point I'd like to make is that development of data over a long period of time really informed advances much later that guided a lot of mathematical research through the 120 years after these tables were first published. And I would submit that the mathematicians that made the effort to develop these tables and to organize this information, they really did an important service. They laid a groundwork for the work that came later. And so for those of you that accepted my challenge to compute the number of primes less than 10 million, so this is the relevant entry of the table. And there are apparently 664,579 prime numbers up to 10 million. And so I have some sympathy that FACL did not do all 664,579 examples. That would probably take a whole lifetime of a person just with pen and paper computation. And so 400,000 is still quite impressive in my book. Okay, so I'm gonna pause here. So for the session chair, should we take questions at the end, or I'm happy to take questions as we go if there are any. I can't see the questions on YouTube, so are there things that I should answer now?
Up to now, no questions.
Okay, then I'll continue. Thank you. Okay. So we got to the end of the 19th century describing the prime number theorem. And so what I'd like to do is I'd like to take a little bit of time to talk about examples in the 20th century. So the examples of the development of data sets and how they informed progress in mathematical research. And so let me go to that next. Okay. And so I'd like to talk about work that was done almost 60 years ago now by Birch and Swinnerton Dyer. Birch is still alive. He's in his, I think he's 91 now. There was just a conference in his honor in the United Kingdom. Swinnerton Dyer passed away 4 years ago. So they did this work when they were quite young, in their 30s. And so basically what they did is that they looked at equations of this form. So y squared equals x cubed plus ax plus b, where a and b are taken to be rational numbers. And so I'll designate these rational numbers by element of q. And we have a technical condition here that ensures that the resulting solution set doesn't have any singularities. So we don't want to have sort of degenerate examples that would look something, they're degenerate examples that cross themselves. And this is something that we do not want to allow. And so that's why we have this condition here. It's to preclude these kinds of degenerate conditions. And so I'm going to erase it. So these are important equations because they have an addition property. This addition property was well studied by Abel and other people early in the 19th century. And throughout the 19th century, it was one of the pinnacles of mathematical work. So elliptic functions and elliptic integrals, they were a staple of research mathematics through the 19th century. We're not going to need all that. We just need the fact that there's if you look at the solutions here, the solutions can be added and subtracted together. So the solutions with x and y rational numbers can be added and subtracted. When you do this, if you start off with a pair of solutions that are rational, then the sum and the difference will be rational. And so this is an operation on the rational solution. So maybe I should emphasize this. So this is an operation on the rational solutions. I don't think I can give justice to actually how one constructs these group operations, except to do some pictures. And so essentially, the relationship that P, Q, and R are collinear, that is, that those 3 points actually lie on a line, that corresponds to a relation that P plus Q plus R equals 0. I should have said that by convention, there's the point at infinity, which sort of points directly straight up. There's a special point at infinity that we take to be the origin. So essentially going vertically to the top of the graph gives us a distinguished point. And so the convention is that when you have three collinear points, we say that they sum to 0. When you have a circumstance where a tangent line meets a third point, you say that the point of tangency times 2 plus the additional point is equal to 0. When you have 2 points that are on a vertical line, the convention is that P plus Q plus is equal to 0. And when you're on a vertical line that is actually tangent to the curve, you say that 2 times P is equal to 0. And so I should emphasize here that for concreteness, I've drawn the points of a typical cubic curve over the real numbers. But the algebra that governs how these addition operations are carried out, it doesn't require that the solutions be real or the solutions be rational. As long as the solutions are defined over a given set of numbers, these operations respect that structure. And so essentially we have an addition rule that is by the instance relations among the points. And so this means that these curves, these cubic curves, y squared equals x cubed plus ax plus b, where a and b are constant, they have a rich algebraic structure that is one of the fundamental challenge questions in number theory. And so here's an example of some points. So I took the case of y squared equals x cubed minus x plus 1. So this is a case where, I guess, a is equal to minus 1 and b is equal to 1. So this is a special instance of an elliptic curve. And so I wrote down the first few fairly obvious solutions with integer coordinates. So here, these are the ones where the coordinates are whole numbers. There are many additional solutions over the rational numbers. So I didn't write all the rational solutions. In fact, we have altogether infinitely many solutions over the rational numbers, but they have a nice structure. So the solution that we indicate here, 1, 1, which is, I guess, the fifth solution on my tabulation, we can use that as a set that generates all the solutions under this addition operation. And so let me just emphasize that this is with respect to the addition operation. Defined via the instance in the previous slide. So let me just remind you. So we have a rule for adding points, and then the assertion that I'm making here, and I'm not justifying it all, is that if I take this special point, I can get all the points simply by taking positive or negative multiples of this given point. And so this is what's called a generator for the set of solutions. Now, in general, there are a finite number of generators for the solutions over the rational numbers. And so this is an important theorem of Mordell. He proved almost exactly 100 years ago that there are, in fact, a finite number of generators for the solutions for an elliptic curve. And so we can try to understand the structure of those generators. And if we ignore torsion or solutions that satisfy n times p equals 0 for some n, if you follow this instance relation and you end up back where you started, an example of torsion here, going back So in this case here, where p plus p equals 0, this is an instance of torsion. But let's ignore torsion. And then ignoring the torsion, the number of generators that we need in order to get all the solutions is an important invariant called the rank. So this is the rank of this elliptic curve is the number of generators that you need to get the solutions, ignoring the torsion. The rank in the example that we just presented is equal to 1. So I'll come back to the next statement a little bit later and give more detail. But we can also look for solutions where A and B are integers modulo a prime number. So looking at, say, integers 0s and 1s, or 0, 1s, and 2, where the prime is equal to 3. And the basic idea here is that knowing, let me sort of write this in the schematic form, that the idea is that the solutions modulo primes, these control the solutions over the rational numbers. So that if you have really precise information about the solutions over all the primes, P, you can basically read off what the solutions are. So if you have a lot of solutions over the rational numbers, you'll basically see that in the growth behavior of the number of solutions modulo primes. And so the first case that I know of where someone actually did a computer search to try to ascertain the structure resulted in some interesting tabulations. So here's an excerpt from their paper in 1963 in the Krellis Journal. And so you see a lot of 1s and 2s, and so they're basically looking at the collection of all solutions and modding out by the collection of all solutions are divisible to, and they're recording a lot of information about those quotients, which includes information about the rank of the curve. And so they're tabulating that information in these pictures. And so if you look closely here, you'll see that there are 2 variables. So there's a B that runs vertically, and the A variables that run horizontally. And this tabulation is for a given value of A and B, where A goes from -20 to +20, and B goes to -30 to +30. Let me write that down. So we have where A and B, as I indicated before, are, sorry to jump around, A and B are just the parameters of the curve. We have y squared equals x cubed plus ax plus b. And so the assertion here is that when A and B are in these ranges, they just tabulated over the, I guess, roughly 60 times 40, maybe 2,000 odd examples. They tabulated the answers. And what came out of this is a really important statement called the Birch and Swinnerton-Dyer conjecture. And this conjecture makes precise how you can do what I indicated here in green. How you can use the solution behavior modulo the primes to control and understand the behavior of the solutions over the rational numbers. sort of a reconstruction result. You can almost think that looking at the solutions modulo primes is a way of sampling and getting data on how the solutions behave over the rational numbers. And the hardest way I can imagine to getting $1 million, I mean, do you want to be a millionaire? Well, if you want to work hard to be a millionaire, you can try to prove something regarding the Bertrand-Swinnerton-Dyer conjecture. It is one of the Clay $1 million problems, and I would be thrilled to see it resolved in my lifetime, but it's hard to be optimistic. Riemann hypothesis is another one. So I think you can see here that a lot of these data-driven investigations in number theory, they really informed important problems at the center of pure mathematics. Okay, I'm going to pause again. Are there any questions, comments?
No. No.
So I want to give you another example, a vignette of how data-driven investigations led to important questions on the structure of solutions. It's quite interesting to me that it was also done in 1963, but halfway around the world, it was done in Japan rather than the United Kingdom. And so Sato and one of his associates, Kanji Namba, who was a logician, they considered, again, elliptic curves. So let me just reiterate here that this is an instance of an elliptic curve. But instead of looking at the elliptic curves over the integers or over the rational numbers, they looked at congruences associated with the elliptic curves. And so let me give you some examples. So if I let p be a prime number, and I take the elliptic curve y squared equals x cubed plus 1, you get all these solutions. And here, of course, the only possibilities for x are x can be 0, 1, 2, 3, and 4, modulo the prime. Those are the only possibilities if you're working modulo prime. If I go back to 5, 5 is equal to 0. So maybe I should just emphasize here that 5 is equivalent to 0, 1, 5. And so the number of solutions, given that you only have a finite number of possibilities, you can enumerate them. And so in this instance, you get 5 solutions. I did another example for a different curve. And here we get 8 solutions for the second curve. Again, over x and y that are taken as congruence classes modulo 5. And so for a long time, people have looked at the solutions of these equations, reducing modulo prime. Indeed, this is what was part of what Bertrand-Swinnerton-Dyer were pursuing. 30 years earlier, Helmut Hasse in Germany had shown that there's actually a structural formula for the number of solutions. And so the first approximation, the number of solutions is equal to the p, the prime. But then there's an error term t of p that shows how far you are from this, from the leading term. And the key observation that he made is that you can quantify this error term. It is bounded in absolute value by 2 times the square root of p. And so we can normalize these so that they fall in a unit interval. And as such, we can think of them as being cosines of angles. And so the question that we come to is, well, how are these sort of normalized distributions? How are they distributed as you vary over all primes? So this is a natural question once you know the general structural results that Hasse proved. And so here is an excerpt from correspondence involving Mikio Sato that they, computations that they did leading up to this conjecture in 1963. So again, they compiled quite impressive sets of data to inform their work. And so sometime later, John Tate, working in the United States, he was at Harvard at the time, observed that for most E, the distributions of these angles tends to be circular. And so that for any continuous function on minus 1, 1, the average of these for p less than x appears to approach this integral. So, and this integrand here is basically just the graph of the semicircular function. And so this is basically saying that you can treat the evaluation at these primes as a way of sort of sampling for this integral. This is a way to compute an integral, a very hard way, using a lot of computations modulo primes, but it gives you information about how these functions behave. Okay, so this is the end of my 20th century, and so now I want to show you the 21st century versions of these big data questions. And so I want to go to Sato Tate again. And so again, as I mentioned, the conjecture is that almost all elliptic curves satisfy the semicircular distribution. It turns out that the case of the remaining elliptic curves is already done before by Hasse, and these two cases here on the right-hand side, these kind of distant cases, they correspond to the complex multiplication. But the behavior of almost all elliptic curves is represented in this picture here. And so this data-driven observation that was found by Sato and his co-workers in 1963 led to an important theorem in 2015. So it didn't take us 140 years. We've actually made a little bit of progress. So this has been proved by Lozel, Michael Harris, Nick Shepard-Barron, Richard Taylor. It won them the Breakthrough Prize. And so this is an important example of how major results came directly out of this analysis. And so Nick Katz and Peter Sarnak, they had a really nice way of thinking about this in terms of essentially sampling of a distribution that comes from understanding random matrices. And so tabulating data on these reductions is like sampling from a distribution. Of course, mathematicians, we don't do experiments. We don't have samples. We don't have random numbers and predictions. But in some sense, the process of computing at a prime is basically for us as mathematicians equivalent to making an experimental observation. And as we make those experimental observations, we see, oh, that was not good. Sorry. Let me just go back. Yes, there it is. As you make those observations, you get data about the distribution. And so this was the observation I was making. I wanted to show you an example of how this can be done. And so I'm going to try to show you a movie. So hopefully this will work. Give me a moment to and so you can kind of see as we compute over more and more primes, you can see these the shape emerge. And so here I'm taking one of the elliptic curves, y squared equals x cubed plus x plus 1, and I'm computing for primes up through 2 to the 40. So that's up through about 1 trillion. And basically just doing a histogram. And you can see this miraculous you have a messy histogram that starts out, and as you run the computations, it really does converge to something that does look like the semicircle law. And so I find this quite remarkable. And of course, there's a massive amount of data. I mean, if you go back earlier, you can see how many prime numbers there are less than 2 to the 40. There's a lot of them. So this is a prodigious computation. Okay, So so my colleague Andrew Sutherland, he had 41 billion data points. If that's not big data, I'm not sure what is. And so basically every one of these instances of this solid tape data and the proof involve, there's huge data sets that support this. And so in higher dimensions, you can also look for these solid tape type distributions. And so by higher dimensions, I guess I should explain that here, instead of elliptic curves, we want to have a billion varieties. So elliptic curve, so this is equal to an abelian variety of dimension 1. And so here we want to look at abelian varieties of dimension 2 and 3. And so this is a problem that had been considered previously by J.P. Serre, and the precise predictions were refined by Fateh, Kedaya, and Sutherland. And so Fateh, Kedaya, Sutherland, and Rotger, they have basically classified all the possible distributions that can happen. So it's not just a semicircular distribution. So there are 52 different kinds of distributions that can occur for surfaces, and 410 different distributions that can occur over various number fields. And so you can try to realize these, and there are massive amounts of computation in actually realizing all these different classifications. So instead of having a semicircular rule, you have much more complex rules. And so just to give you an indication, here are some examples of sort of a rogues gallery. So for the experts here, I'm only showing the trace in the solid tape distributions, but for a whole bunch of different cases. And so they're not all semicircular, but they show that we're sampling interesting distributions in all these cases. And so the computations to show that these cases actually arise in practice and which ones arise for examples over the rational numbers, they're prodigiously complicated, involving massive, massive data sets. So I think Gauss would be proud to see the complexity of the data and the structure that emerges in this analysis. And so now I'd like to come closer to something that that we as a group are pursuing. So we no longer have these large tomes that incorporate all this data. We have web databases, and I encourage you to take a moment and explore these web databases. It's the L functions and modular forms database, and it aims to have a systematic exposition of a lot of these key number theoretic ideas, especially those connected with elliptic curves. It was officially launched in 2016, so I'm proud that ICERM played a bit of a role in helping to get this underway. Of course, this builds on earlier databases of elliptic curves, due to Cremona, and modular forms, due to Stein. So it's not like we started from nothing in 2016, but it's really grown quite dramatically in the last 6.5 years that people have been working to try to develop this as a systematic resource. And so this is an effort to store lots of different data that is relevant for current research in number theory. And so I've listed a whole bunch of the typical data sets. And it includes some of the things that we talked about. So there's certainly things with elliptic curves. I wish I could define L functions, but I couldn't. There's things over finite fields. So there's quite a lot of course, there's the Sato-Tate structures. So these are all things that we've seen. And the L functions in modular forms database really attempts to try to take the calculations that people all over the world have been doing and put them on a systematic footing. And so I showed you an elliptic curve before, y squared equals x cubed minus x minus 1. And every elliptic curve has its own page. One of my colleagues, he said that this is sort of like social media for math objects. So everyone has their page with their personally valuable information. And so all the things that we have tabulated, from the structure of the groups to the equations to the integral points, here you can see these are the points that I enumerated for you. And of course, I just took them off the database. I didn't compute them myself. But these are the points that I showed you early on. And lots of information that is relevant to things like the Birch-Swinnerton-Dyer conjecture. So you see here the BSD invariance. These are the things that actually go in the precise formulation of the Birch-Swinnerton-Dyer. All the different things that go into the shape of the functional equation. We present them here. And we try to link the objects that are related to each other. And so number theoretic objects are linked to their friends. And so here is a modular form that is directly linked to the elliptic curve I just wrote down. There's a deep connection between elliptic curves and modular forms that is due to a theorem of Wiles and Taylor. And this is called the Taniyama-Shimura conjecture. And I guess I should say, because this is a public lecture, this is the main input into the proof of Fermat's last theorem. It used these conjectures. And so these are we try to have all these objects be closely related to each other. So we have big data, and we spend a lot of time organizing the big data so that there's some meaning and structure that can be extracted from it. And so this has been, it's a resource all over the world. We're proud to have people in many, many different countries using this. And so the growth is quite encouraging. Many people use this in teaching, and people use it in research. If you have something that looks like it might come from an elliptic curve or a modular form, you can check in the database and see if anyone else has found it before. And I just wanted to give a shout out to two of our members of our collaboration, David Rowe and Edgar Costa, who completely rebuilt our database in the last couple of years, and have made it much more substantial and better organized and efficient. And so we're working to add lots of new content. So we're classifying groups of various kinds. So we have started with 92,800 groups, and currently we have over 257,000 groups, and lots of subgroups and conjugacy classes. These are massive computations, and so we aim to both encode all this information, and from the way that the information is organized, to show the structures about how various objects are related to each other, just like we did before. And so hopefully we can do almost all groups of order up to 2,000. The thing I didn't even realize, having taught group theory for 25 years, is that essentially all the groups in the universe have order 2 to the n, all finite groups. If you look at enumerating the groups up to a given order, there are a massive number of groups that have order 2 to the n, so many that we can't even classify them. And so this becomes clear as you develop these databases. There's some classes of groups that have, order 1024 that are really out of reach. There's 49 billion groups of order 1024. It'd be hard even for us to classify them. And we're also constantly collecting new data for homogeneous curves. So this is basically what sort of is the input for the Sato-Tate type distributions. Is massive computations of small genus curves. And so this is a chart showing how my colleague Drew Sutherland basically took over 600,000 cores from Google on a quiet day when they had no one else using them. And then this is massive computations for curves of genus 3. And this was one of the ways of verifying that the distributions that I showed you actually can be realized in nature. You have to find examples of curves that have the given characteristics. And this is how these examples are found. So I am running low on time. And so I'm just going to show you one last theorem that uses massive data, which integers can be expressed as a sum of 3 cubes. Obviously, 3 can be expressed as a sum of 3 cubes, 1, 1, 1, or 4, 4, 5. 4, 4 minus 5, but is there another possibility? And here's the answer to this challenge. This is the next smallest solution after 4, 4 minus 5. I think these have 16 or 17 digits. And so this is another instance of large data searches that inform solutions to problems in number theory. And this involved using almost 4 million hours of computation, 4 CPU centuries to solve these problems. So this is another instance where a massive parallel computing allows people to solve problems that they wouldn't be able to solve otherwise. And now I just wanted to thank my colleagues in the Simons collaboration that made this all possible. Our research scientists who are all contributing to this work were listed here. And our alumni, including Do-Young Kim from Seoul National University. We're really pleased to have people who have worked with us taking up faculty positions all over the world. And so this is some of the people that have contributed to the work I talked about. So, and some of our senior colleagues who are helping guiding what we do. So I've gone over. I think I've already used the 50 minutes that I was allocated. So I wanted to thank you very much. I appreciate the opportunity to tell you what you've been working on. And I would welcome any questions or comments that you would have about what I presented. Thank you.
Okay, thank you. Thanks to Professor Brandon Hasses for his wonderful lecture. Are there any questions or comments? There are no questions in YouTube site, in 채팅창. Actually, I have one question. So,
yes.
How about the case for the abelian variety of dimension 4? Dimension 4 case. Are there any attempt to...
I think for abelian varieties of dimension 4, the techniques that have been developed by Sutherland and Fité, they don't give... I mean, well, let me go back to the slide where this is discussed.
Yeah.
And just to make the point that there is a bit of a combinatorial explosion. Give me a moment to move to the right place. So,
yeah,
in dimension 1, there are 2 distributions. In dimension 2, there are 52 distributions.
Yeah.
In dimension 3, there are 410 distributions. And I don't even think we have an estimate for the number. So I don't think that we know how many distributions there are in dimension 4. So let me just write this at the bottom. For dimension 4, I'm not sure how many cases.
Okay, thank you.
And so let me just say one other thing. One thing that would be difficult in dimension 4 is that we cannot necessarily realize the distributions by looking at curves. Curves are really easy to write down. If you ask me to write down a genus 2 or a genus 3 curve, I can pull out my piece of paper and easily write all the representative equations. For abelian fourfolds, they don't necessarily come from curves. And so this makes it much harder to do the kind of enumeration that was done before. The fact that curves of genus 4, they depend on 9 parameters, and abelian varieties of genus 4 depend on 10 parameters. It means that we would need to have another mechanism to try to do an exhaustive search. And we wouldn't be able to take the straightforward search, looking at all the quartic plane curves with coefficients of a certain size to try to saturate the possibilities for the distributions. So I think it's much harder, and I don't even think there's a clear expectation for what the answer might look like.
Thank you. Thank you for your answer. Yeah. So, this is the end of Professor Brandon Hassett's lecture. So let us thanks again to Brandon Hassett. Yeah. Thank you. And
thank you very much for giving me this wonderful opportunity. I very much appreciate this.
Okay. Yeah. I will say in Korean. Okay. 예, 이상으로 키아스 대중강연을 마치도록 하겠습니다. 긴 시간 함께 해주셔서 감사드립니다. 예.